This presentation is the first collaboration between the Athenaeum Symposia and the Spectrum Lecture Series, the Frank Islam Athenaeum in the Spectrum Lecture Series. I'm Dr. Richard Pyers. I'm a professor of chemistry on the Germantown campus, and we formed this joint sort of presentation because we recognize that a lot of the problems important for society today can be best addressed if we look at it from very many different disciplines. And all of the answers to all of these questions are important to us all. So that's why we sort of are doing this, because I think it's a really good opportunity. On behalf of Germantown campus Interim Vice President Mohammed Kianome, I'm honored to welcome you to today's presentation. I want to say first that I think we're all really fortunate in the Montgomery County area because we live in a very intellectually vibrant area. We have access to the resources in DC, in Baltimore, and everywhere in between. We're also really lucky at Montgomery College because we have the resources to have presentations like the one we have today, in large part due to the generosity of people like Mr. Islam. On a sort of more personal note, I want to mention that all of us are really fortunate to have the resources and time to come to an event like this. To paraphrase Sir Isaac Newton, we're able to do what we can do because we're standing on the shoulders of giants. I think we should pause and reflect a few moments and think about all the people who've come before us and who have borne our weight on their shoulders and let us do what we're doing today. The Athenaeum Distinguished Speaker Series is made possible through a gift from philanthropist and civic leader Mr. Frank Islam. The Spectrum Lecture Series was founded by Emeritus Professor of Chemistry Robert Coley. This year, the Athenaeum speakers are all exploring the theme of social justice and community wellness. You can find out more about the Athenaeum Symposia if you go to the Montgomery College Athenaeum website. The same thing for the Spectrum Lecture. You can find out more about the Spectrum Lecture on the MC website. It's very important for us to acknowledge all the people who are working really hard to put on the presentation today. I want to start off by mentioning the MCTV producer, Mr. Peter Pereira, Miss Vivian Chang, and Miss Tonya Adelman coordinate all the administration stuff, and Dr. Fiona Glade, Dean of Communication Studies, English Language for Academic Purposes, and Linguistics, and the curator of the Athenaeum series. They all have worked really hard for us to do what we can do today. And with that said, I'll hand things over to Nafisa Azizi for a few minutes.
Good evening and happy Ramadan to everyone. My name is Nafisa Azizi, and I am the STEM Ambassador Advisor for Montgomery College. So tonight I'm just going to mention a little bit about what we do and what sort of activities are involved at Montgomery College. So who are STEM ambassadors? Dedicated and passionate MC students, volunteers committed to promoting STEM education for all, organize and facilitate STEM activities and events in the community, assist with STEM programs at MC and in the community, inspire others to pursue studies and careers in STEM fields. This semester, we have about 20 STEM ambassadors, and some of them are here with me tonight and volunteering in this event this evening. So what STEM ambassadors do? Outreach to schools, community organizations, and other groups, provide engaging and exciting STEM projects and activities to students, promote STEM education among all students in MCPS, bridge the gap as a role models for underrepresented students in the STEM field. And these students are STEM majors, and they are in our STEM Scholars Honors Program. They win awards and internships. They participated in undergraduate research and STEM competitions. And they participate in encouraging active engagement and participation with fun STEM activities. So STEM Ambassadors in Action, what they have done so far this semester. They were involved and they participated in Sonia Guralski Day, which is one of the events at community at Montgomery College. They basically were involved. They worked closely with program organizers to create engaging and challenging projects. They helped organize and develop mathematical and programming projects for the students who participate in the program. They also volunteered at Maryland Science Olympia. That was a second event that they did this year. STEM ambassadors were volunteered for this program, helped plan and execute activities like flying, trajectory, and parachuting for this event. And growing the STEM ambassador program. So what are we planning in the future, basically? Build new relationships with MCPS, Title IX schools, local industries, local nonprofit organizations, local colleges, and then also strengthening the existing partnerships, which is youth programs at MC Lab School, which is for younger kids at the college. They're also volunteering some hours there to help them with creating some videos with them, to posting on YouTube, so these younger generation can benefit from these videos. And they're also seeking grants and funding resources for future activities connecting Montgomery College with MCPS. So partnering with us, students, anybody can apply for this. So we do have our own websites. The application is available for anybody interested. We also have some flyers outside that you can grab one and you can apply. And if you are one of the candidates, you will be selected for the program. And then also event organizers, they can request, like tonight, you can just reach out to me or you can email to STEM ambassadors at montgomerycollege.edu with your event, and then I will connect you with our ambassadors, and you can benefit from them as well as they benefit from being there to represent MC. So for more information, you can visit our website at montgomerycollege.edu, and thank you. So now I hand the mic to Senior Vice President of Academic Affairs, Sanjay Rai.
Thank you, Nafisa, and Ramadan Mubarak to you and everyone else. I'm delighted to be here. Thank you to Dean Fiona Glades, who runs our Frank Islam Athenaeum Symposia, and very thankful to see so many students and faculty in the audience. I don't know, the topic is mathematics, but that doesn't mean you have to sit in the back rows, right? It's not really a math class, it's going to be fun. So, well, it's okay, you can hear us, right? A very special day today. We are bringing Frank Islam Athenaeum Symposia back to campus. Very good. It became virtual during the pandemic, just like so many other things. So, some sense of normalcy. And also looking at collaboration between Spectrum and Athenaeum Symposia. That's again a very, very powerful and very appropriate speaker to bring the two aspects together. I came to Montgomery College 19 years ago, almost 19 years ago in 2004. And some of you know that I am also a mathematician and a senior vice president at that time for academic affairs. Dr. Shortle Galato, she knew I was a mathematician and she gave me a book to read. And she said, you would love it. It's written by a mathematician. And it was Death of Vishnu by Dr. Suri. Fell in love with it. Excellent. Fast forward, I came to this campus in 2009 as Vice President Provost of the campus. Some of you may still remember that. And at that time, there were strong urgencies. We have a hospital conversation going on, and our bioscience education building was delayed. So the lot of conversation about STEM. And folks who were in arts and humanities always felt that area needs more attention, and rightfully so, and attention from the leadership at campus, deans, provost, and everyone else. And in spite of serious emerging issues in hospital and science building and all, we went ahead and wanted to create another lecture series. And even before Frank Islam came forward and provided resources, and we named the series after him, one of the first speakers, potential speakers that I contacted, it was 2010, I think, 10-ish. One of the first speaker was Dr. Suri. And he wrote to me that he's going on sabbatical, he's working on a book. As soon as that is over, and fast forward, things changed. I moved to another position, and then I heard from him again that hey, I'm available, and I connected him with Fiona, and we are here today. So really, it's a very, very special day for us, and I'm going to introduce Dr. Suri, who is a professor of mathematics, a researcher, novelist, was born in Mumbai, India, formerly known as Bombay. And for full disclosure, my wife is from Mumbai, so I have to say good things about Mumbai. It's a great, great city, great place to be. We enjoy our time there. We visit almost every year. After starting out as a physics major, he was encouraged by his favorite professor, an algebra professor to whom his new book is dedicated, to switch to math. Dr. Kanamui, that's the way it happens. Dr. Suri earned his BS in math from University of Mumbai, then moved to the United States, where he earned both his master's and PhD in mathematics from Carnegie Mellon University. In 1983, he became a mathematics professor at the University of Maryland, Baltimore County, where he is now a distinguished university professor of mathematics and also an affiliate professor at the UMBC Asian Studies program. Dr. Suri has served as principal investigator on numerous grants on numerical analysis, including support from the National Science Foundation, the Army Research Office, and the Air Force Office of Scientific Research. He has served as associate editor for the Society of the Industrial and Applied Mathematics Journal on numerical analysis and on the Journal of Computational and Applied Mathematics. He's also an active participant in the finite element circuit. Dr. Suri has written numerous books, which he has called his extra mathematical infidelities, including a trilogy of novels, all named after Hindu gods, The Death of Vishnu, I mentioned that earlier, which is an internationally bestseller, The City of Devi, and The Age of Shiva. His fiction has been translated into 27 languages and nominated for countless awards across the globe. He won the McCritic Prize and the Barnes & Noble Discover Award, among others. And his fiction was longlisted for the Booker Prize and shortlisted for the PEN Faulkner Award, LA Times Book Award, PEN Hemingway Award, and the W.S. Smith Literary Award. He has been a fellow at the Virginia Center for the Creative Arts and the MacDowell Colony, and was the winner of the 1998 Jenny McKean Moore Residency Fellowship from the George Washington University. Dr. Suri has also published articles on mathematics, India, and LGBTQ+ issues in Granta Magazine, the Washington Post, and in the New York Times, where he was appointed as a contributing opinion writer. Dr. Suri's latest book, which is the subject of his talk this evening, is titled The Big Bang of Numbers: How to Build the Universe using only math. He takes readers, even non-math people, on a thoughtful explanation of mathematical concepts using entertaining examples, including the world of crochet, creationism, and fine arts, with plenty of illustrations. Many of us who are in mathematics know that when you move from a journey of your college math to the abstraction, sometimes you see a lot of beauty, like understanding what is countable or rational numbers or are countable, or Cantor's diagonalization process, or the fact that infinity can come in different sizes. That's where some of us became interested in mathematics, but that's also a bridge that's hard for some of our students to cross. And often, sometimes we lose students in that process. So we really appreciate these kind of explanation that can sometimes fill the gap, make folks interested in mathematics, especially on the abstract side of mathematics. In an interview with Telegraph India, he explained that he first started thinking about writing a book on maths for the general public in 2008. He was going to call it The M World. And in an interview with the Vice Owl, he described how he brings together his two worlds of mathematics and fiction writing. If you're writing any type of nonfiction, be it a newspaper report or research paper, a good piece of advice is always find the story. Indeed, this is surely one of the most successful ways to get any message across. Who doesn't like a story? We all do. So we look forward to hearing from Dr. Suri now about his story. Dr. Suri.
Well, first of all, thanks to everyone here for organizing this, for inviting me, and also for being so patient for all these years before I could actually come here. And thanks also to all the people who are here in the audience. I promise this is going to be a fun talk. So those of you who are sitting close to the exit so that you can make a quick getaway, just wait till I have my talk in gear. And the talk is going to actually be about two different parts. Usually I just talk about my book, but today what I want to do is also tie it to the topic of the Athenaeum series, which is social justice for this semester, and how math really figures into that. You don't usually equate or associate math with that. So let's see, I'm just going to bring my talk up. So that's the topic which you've seen. And what am I going to talk about? Well, first thing is, anytime you talk about math, nowadays especially, what we hear about is bad news. And you either hear about all these curriculum fights, or you hear about Florida banning, certain things in the curriculum, or Algebra 1 not being offered in schools, and so on. And the biggest bad news in the last few years, and this is a real issue, has been the pandemic. And some of you have probably encountered this too, the switch to online learning. And that's been really disastrous, both in reading and in math. But if you look at these diagrams, you'll see that math is much worse, because there's a national exam called the NAEP given to the entire country, and that measures how people are doing in math. And it's given in the 4th standard, in the 8th grade, and in the 12th grade. And the results from the 4th and 8th grade basically show a huge decline in the last 2 or 3 years. And you see that this graph has been, the math graph has been going upwards a little bit, but then the last 2-3 years, it's really declined by several points. I was talking to a student who is also a math teacher at a school in a county in Baltimore. Not in Baltimore County, but another county, and he was telling me about how arresting a particular headline had been in Baltimore where they actually took 23 schools and they found that not a single person could be found who was proficient in mathematics out of these 23 schools. And then there were another 20 or so schools, and there were only like one or two students in each of these schools. So again, this is just a huge problem. Why is this a problem? Well, some statistics, when you see these declines, the decline is often not the same in different groups. So if you look at this, and let's see, if you look at how this has been going on in terms of different ethnicities, for example, you will see that the trends, somehow this isn't coming up that easily, but you will see that, this is, for example, well, somehow this isn't coming up, but if you compare different races, for example, you will find that the decline for minority students has often been a lot worse than for white students. It's also tied into economically disadvantaged groups, where again, the decline is much stronger. It's the weakest students who have found the most decline. One reason for that, again, it's highly tied to economics, because if you look at a survey that was given along with this, if you looked at the lowest 25% in terms of how they were doing in mathematics, they reported that they had significantly less access to the internet and to quiet studying spaces. And those two factors, again, compared to the highest performing students, those two factors, again, suggest that the economics is a big role, that people don't have proper internet access, people who don't have quiet studying spaces will do worse. So this is something that the statistics bear out, and this is very typical of whenever you have any kind of comparison like this, it is often disadvantaged groups that do worse. Another kind of way of testing this is SAT scores, and class of 2020 average scores for Black and Hispanic students is a lot lower than for white or Asians. So you find this differential performance or achievement, differential proficiency, which is exactly a social justice issue. Because what happens? What happens later on is that if you are not good at mathematics, a lot of things get shut out for you. For example, there was a survey a long time ago where a significant people, it was almost like 80%, cited not being able to do well in Algebra 1 as the reason that they decided to drop out of school. So that's an amazing statistic. That was from 2010. There's other statistics that show that graduation is one thing, but also jobs. If you don't go into college and you're not prepared, then you have to either struggle with remedial courses, or you have to take additional courses to make up what you should have learned in school. And that, again, is a big challenge. And so, again, students might say, hey, I'm not going to go into STEM. I'll just do something else. And the only problem with that is, it's fine to do whatever, but if you look at the whole nation and most of the minority students or most of the disadvantaged students are not going into STEM, you have this imbalance. Also, STEM jobs typically pay more, both in mid-career and in starting salaries. So you have this economic inequity that is sort of built in along with this problem with achievement in mathematics. And it's not just mathematics, it's also other science subjects, but mathematics seems to be the one that is most dire. So what are the causes? So people have come up with many causes. There's a lot of research done in terms of teaching methods, and some people are against whatever newer methods are being taught, and some people are for them. There is a lot less emphasis on rote learning. There are new things being put out. And you saw that those scores were going up very slowly but steadily. So there is some, some good news there that things are being used up, that things are improving. One of the big problems is teachers in schools. Often they are not fully, especially lower grades, they might not be fully qualified to teach mathematics. And there's a lot of problems of attracting good talent. This student that I was talking about, he is a teacher, but he's also doing a master's because he doesn't want to keep teaching. He wants to go on to something else. So that is a big issue. How do you retain the brightest and best teachers? So that's a big issue. And then there is something that students will often encounter, and that is what is called a fixed versus a growth mindset. And this is, there are many, like if people have gone to professional development seminars, you'll often hear this. A fixed mindset basically says that, okay, if I fail at something, then that's because of me, because my God-given sort of abilities are such that I've reached the end of them, and if I failed at math, if I'm not doing well in math, that's because I'm not a math person. This is often accentuated when you hear people like parents or elders also saying, hey, I've never been a math person. I can't do this. I'm not a good person at math. So that kind of attitude kind of just percolates down. And this is something that's a real problem. The growth mindset, on the other hand, those kinds of students will think, hey, if I didn't do well in this test, it's because I didn't study enough. And the corollary is that I should try harder, and maybe I'll do better. So there are ways to try and switch that kind of thing, but that is one of the things that have been identified in terms of people who, as students, might just give up at some point, say that, hey, I'm just not a math person. And so that's an attitude that also has to be worked on. But these causes don't get to a sort of root cause that I feel is really at the root of everything. And that is, society in general, the society we live in, has a very dysfunctional attitude, relation to math. What I said about, oh, I'm not a math person, you usually don't hear people say, hey, I'm not a reading person, ha, ha, ha. That would be kind of strange. But a math person, you can be even boastful about that. Hey, I've never been good at this. So that's a kind of strange thing that these same people will then turn around and say, hey, how come the results are so bad? You find that there's some examples. Math, doesn't really have a cultural profile. Like if you think about art, okay, if you want to appreciate art, go to a museum. You'll be able to see all the art you can. Think about music, you can go and hear a symphony. You can listen to the radio. But think about math, and people often immediately will start thinking about, hey, calculations, we have to learn how to multiply or something like that, and it's drudgery. You don't often see examples in the media, for example. It was a wonderful paper I was reading just before coming here about this researcher, Jennifer Hall, who looked at all the ads in newspapers and magazines over 20 years. And tried to identify which ones used math as a meme of some sort. And first of all, there was almost nothing. So, that's just, math has very low visibility in our society. But more than that, she found that out of the ones that were things that she could identify, math was often treated in one of two ways. Either it's only understood by, real supernaturally gifted people like Einstein and so on, and it's not for ordinary people like us, or it is identified just with school mathematics. And Sanjay was talking about school mathematics being, just very drudgery-related mathematics. You're learning how to add, or you're learning how to multiply or divide, long division. That's the big thing. And you're not really getting exposed to parts of the subject that are interesting, that are joyful, that are more like games. Professors or teachers in school will often tell me, we'd love to do things like that, innovative things, but we have to finish the syllabus and we don't have any time. So all of this is tied together. The cultural idea of math. You don't think of math in the culture. It's really not very visible. One example is there are 35,000 museums in the US. How many museums do you think are solely devoted to mathematics? One, exactly. There's one. It's the National Museum of Math in New York City. And that opened about 10, 15 years ago, and it's been doing well. Of course, there are science museums, but those two are much smaller in terms of the number of art museums. So I'm just saying that as, just to see what it means to have a cultural profile. Newspapers, bookstores, well, I know this for a fact because I just have a math book out. And I went the first week and I said, okay, I'm going to look at, this was in a Barnes & Noble in New York City. I said, where's my book? It'll be in the nonfiction section. No, it wasn't there. Is it in one of the stacks? No, it wasn't there. It had just come out like a week ago. And then I went to the first floor, wasn't there. And I went out to the second floor. And there in the science section, listed alphabetically so that only the spine was showing, were 2 copies of my book. So it was like, okay, if people don't see it, they aren't going to even look at it. So it's that kind of attitude where there's a lot of gatekeepers who are not really, they're not math people, and they figure that no one's going to be interested. And so that, again, leads to lower visibility of mathematics. And we've already talked about that. So how does this affect students? Why does this cause such a problem? First of all, let me just tell you, math is hard, as everyone knows. Even for me, for people who are professors, for anyone, math is usually hard. When I was learning math, drilling myself in tables or whatever, it took a while. It takes practice. And the problem is if there's less evidence of it in the culture around you, and I'm talking about the most disadvantaged people who might have the most shaky support system. If you don't see it around you, and the only idea you get about its usefulness is your teacher telling you, okay, don't worry about uses right now. You'll be able to use it to get a good job. Pennies in heaven. So it's some future promise. And you don't really see how it's arising in your world, in society, in nature. And then you get this, I'm not a math person drill from people. Well, why not just join in? Why not just give up? And that's what unfortunately happens. So what we need is really something that's going to be a huge, to really get at this problem, you really need some sort of social change. And I feel that educational refinements will help, but they can only go so far. You need something more at the grassroots level. And we can all do a little bit. So interestingly, and I should just say, this is where that tie-in with social justice comes in. This is how mathematics needs to be, it's a very crucial thing, and people often overlook it, but it needs to be somehow in our public discourse, where we are really talking about it as a cultural force, not just an educational force. How to do that? You might not know this, but in a few days, it's going to be April, and can anyone tell me what April is? Is what? Pi month? No, Pi was in March. Pi Day was in March. So what is April? It's Math Awareness Month, which, no one is aware of, unfortunately. And in fact, there was a lot of controversy because the statisticians said that, hey, we are not included. So they actually switched it to Math and Stat Awareness Month. So if anyone asks you, it's no longer Math Awareness, it's Math and Stat Awareness Month. This is April, and this is coming up. And what the good news is the following, and this is where my idea comes in. You might have heard of the Pew PEW Foundation, and they do a lot of polls. And they did a poll in 2017, and what they found was that 58% of US adults liked math in school, and the other 42% did not. But 58% is a huge amount if you think about it. So even with all the bad rap and everything, still like a large number of people actually enjoy their math when they look back to it in school. Now this is millions and millions of people, and I'm not going to go into that, but this breaks it up by STEM and non-STEM and so on. But here is my idea. If each person, each one in this room, for example, certainly the STEM ambassadors, whom, that's a great idea, and I hope you can participate. Maybe we can, email and do something jointly. But the idea is in April, think about why you liked mathematics, what you liked about it, and talk to someone about it. And it can be just a kid that you know, some student. It could be your spouse who hates math, for all I know. It could be anyone, but just getting that into the discourse. And you might say, hey, that's very simplistic. That's not going to make any difference. It will make a difference for the person you talk to. That will make a little change. So can we recruit these to 58%? And again, this is not something that's going to happen overnight, but I just want to plant this idea as something to think about, that there is this large population that is sitting out there that has enjoyed math and that is capable, perhaps, of transferring these ideas to students. Now, I'm not talking about, there's the poster, usually this Math and Stat Awareness Month is really aimed at the top students, trying to attract them to do math as a career, math, unraveling complex problems. And I feel that with what's happened with the pandemic, the best idea right now is to concentrate not on the successes that math has shown, but on the failures, like all the people who are really struggling with it. So this is what I think. Talk about math. Math could be a math puzzle or a game. And the key idea is, what is it that you like about it? You want to convey this idea of exploration and fun. Now, this is not the same as getting proficient in math. So this is one thing I want to emphasize here. Math has two parts to it. It's like the left brain and the right brain almost. One part deals with getting formulas in, getting better at calculations, being able to do complex problems. And that's very necessary. That's the skill that you really want to have, at the end of everything. What you need, what is really missing, the missing part in all this, is having interest. Like, what is going to sustain you? Like, if math is this hard journey that you have to take by yourself to get better at and more proficient, what is going to keep you going on that journey? And for that, what you need is some sort of fun, some sort of, joy in what you're doing, some sort of exploration. And that's the part that I'm hoping that we as a society can pay more attention to, this cultural aspect of math. The proficiency we would still have to leave mostly to schools or tutoring, which has been known to help. And this is some time back in 2013, I wrote an article about this in the New York Times, and it was how to fall in love with math. And the idea was that math doesn't have to be about calculation. The calculation is important, but we're really talking about the other parts of math that you don't really see in typical high school educations. So that's what we want to access. That's what we want to spread. And what I'm going to do is I will, so that book actually, this is the book that I ended up writing. So this was in 2013, the article came out. And it was very interesting because just about the same time that the day that the article came out, it really got a lot of responses. And they used to have a thing where you could see how it was being emailed. It was a popularity contest. And my article kept going up, and became the most emailed for the day. And then around Friday, I realized that it was number 3 for the week, most emailed for the week. And by Saturday, it was number 2 for the week. And I was saying, wow, it's going to be number 1, most emailed for the week. And just then, the Pope started making all these controversial statements about abortion and homosexuality and all that. all these liberal statements, and he came bounding from behind me and jumped over me and took my number one spot. And that, I don't have anything against him. In fact, I even sent him a copy of my book. And I'll tell you what he said at the end. But it made me realize that something like religion is very good at having a really high cultural profile. And with religion comes physics as well. They're very good too, because physics is related to questions of origin and so on. So math is much, much harder to really disseminate and to make popular. So that's the reason why I started writing this book, just starting from this article, how can I make math more enjoyable? What is the story? Try to see if there's an actual story in mathematics. So what I'm going to do is, I usually give a talk about the story that's based in this book. I'm just going to pluck out a few examples and show you, just in the spirit of what can be done when you are trying to convey this idea of math being everywhere and math being fun. And one of my favorite, I'll give you two examples. One of my favorite examples is how do shells form patterns? And you have these shells that have various kinds of stripes and so on, and the shell at the bottom is the most interesting. Look at how complicated that pattern is. So the question is, how does that happen? And it turns out to be very mathematical. And I love this example because it doesn't have any numbers in it. Because math without numbers. Math is really about ideas rather than numbers. And that's something that is very hard to get across, but this is a great way of doing it. So let's see if I can get it across here. So what happens is the way that shells form patterns is there is a ridge that keeps getting more and more deposits of minerals and keeps extending. And the way that ridge forms is there is the mollusk, the living creature inside, and that has a sort of lip, and it keeps exuding more and more minerals, and that's how this shell forms. Now this lip that goes there, it curls around and comes like that. This lip has many cells on it. And these cells can be switched on or off. When they're switched on, and when they're exuding this mineral, then the mineral comes out colored. When they're switched off, then it just comes out plain or blank. It'll come out white. So the shell has some binary kind of thing going on where this lip is, each cell is either giving you a colored mineral or is switched off and is giving you a plain mineral. So think about what would happen in this first scenario where a few cells in this lip always remain switched on. So these cells always remain switched on. Then what will happen is that as you go, as it keeps extending, this takes many days, many weeks, many months, but for each time step, the cells that are on remain on, and the ones that are off remain off. So what you will get is, you can see, you will just get stripes that are perpendicular to that lip. That's relatively easy to see what happens. Okay, so then the question becomes, how do you get stripes that are parallel to the lip? What is going to happen for those stripes? Any ideas? Yeah, so what happens in this case is that you have a certain number of cells. Every cell along the whole lip, for a certain amount of time, it switches on, gives you a black or a colored stripe, and then for the next interval, it switches off. So it gives you a white stripe. Then all the cells again switch on, all the cells again switch off. So it's black, white, black, white. So you get these parallel strips. So that's another type of shell. Now here's the interesting question. How do you get something so complicated? What possible thing could be going on? Is there any math to this madness in some sense? It seems completely disorderly, but it's still orderly. So how does this happen? And it turns out it's a very simple algorithm. There's a nice model that says that it's not just all these shell patterns can be really explained with a very simple thing. And that is that depending upon what the cells were doing in the previous step, that will affect what they do at the next step. And it's not the whole row of cells. It's only 3 cells. It's only your immediate 3 cells. Yourself, let's say I'm one of the cells, and my 2 neighbors. So what the 3 of us do at this step will affect what the middle cell, that is I, do at the next step. So this is a very interesting thing. It makes it much simpler to kind of process, and it becomes a nice kind of puzzle that you can actually do. And so here is a simple rule. Now, this might be hard to read, but it's actually just saying the following. If my left side neighbor is turned on, at the next step, I will turn on. If my right side neighbor is turned on, at the next step, I will turn on. If I am turned on, at the next step, I will turn on. If 2 of them are turned on, I will turn on. These 2 are turned on, or those 2 are turned on, I will turn on. The only time I will turn off at the next step is if both I and my 2 neighbors are turned off, then I will just remain off. Also, if all 3 of us are turned on, then that's too much pigment going, and I need to conserve it, so I will turn off at the next step. So these rules, they're, again, not so hard. It's basically it's only turned off if all 3 of us are turned on or all 3 of us are turned off. So look at what happens. And I was debating whether to give everyone a piece of paper so that you could do it. But let's say you start with a single cell that is turned on. Everything else is turned off. What will happen at the next step? Well, at the next step, and these are very small, I apologize, but at the next step, notice that since I am turned on, the next cell, I will be turned on for the next time. If I look at my neighbor, since this person is turned on, therefore I will be turned on at the next time. And if I look at my neighbor on this side, since this person is turned on, I will be turned on at the next time. So there will be three cells that are turned on. What happens after that, though? Notice that since the 3 cells are turned on, I will have to conserve energy, and I will turn off. So I will get a blank there. And these 2, you can work it out, will turn on. And then if you look at the rule again, you'll see at the next step, everything will turn on. Now imagine doing this as an exercise on a graphed piece of paper, and I've done it actually with students, and it usually goes pretty well, where you try to figure out what the next few steps will be. And it turns out it's not very hard to figure out, and it's a purely logical thing. It's like a fun game almost. And you can see that what you will end up with if you do several steps is this pattern. Now this pattern, does anyone know what this is called? Sierpinski. It's called the Sierpinski triangle. And it's an example of what is called a fractal. And if you did this over and over and over again, you would get this amazing pattern. And the interesting thing about this pattern is that if you take a piece of it, it looks exactly like the larger pattern. The same pattern is being repeated at different scales. And also, if you were to do it over and over again, you would find that, if I threw a dart at the lower thing, it's so full of holes that the dart would just go through. So there's no area in it. So it's a very interesting kind of pattern called a fractal. But the question is, our shell was much more complex. It wasn't just this nice pattern. It was like triangles were going here, they were coming up, going off, coming on. What's happening there? How come we don't really see that perfect pattern on a shell? You see something all mixed up. And it's actually a very simple explanation for that. And that is that when the cell first starts, it's some sort of randomness that is present in the cells that are switched on. So the first time step, it's not just that one single cell is switched on. This one is going to be switched on, the next one switched off, then 2 of them switched on, then the next one switched off. So there's going to be some random pattern. And if you actually start with a random pattern, you get something like this. This is computer generated. Compare it with the first one, and you'll see, hey, pretty close. So that's pretty amazing that a simple rule like this can explain what happens with math, what happens in a shell. And you can come up with all sorts of rules and, come up with these patterns. And it's a nice kind of challenge to give someone and see what happens. For example, this pattern, it starts off funny, but then it starts giving you stripes. So it's interesting that different things can generate stripes. And there's a whole bunch of these that you can come up with. So anyway, that's one example that I love talking about. And I figured this would be too big an audience, but I actually have some of these shells, and they're pretty neat to look at. So, in a classroom, I would give those out. This is my second example that I would like to just show you. And this is about ants finding the shortest path. So these are both from my, things in my book, for example, both of these. So here's a picture. You've probably seen ants, they're going from their nest and they're going all around looking for food, and then somehow they find some food, and there'll be different tracks that they're taking to get to the food. And what you will see, though, is that after a while, the longer path seems to have fewer and fewer ants. And the shorter path will have more ants, and eventually there'll only be one path. The longer path will have just gone away. So how is that working out? What's going on there? How are they actually mathematically optimizing this? And it turns out to be a very simple algorithm. All they do is, as they go towards on their path, they keep dropping pheromones. And these are things, these are what are they? I don't even know how I describe them, but this is something that other ants can sense, can smell, and depending on those, other ants will sense those and will follow the same path. Now, if you have two paths, the longer one and the shorter one, there'll be more ants that go back and forth on the shorter one just because it's the shorter path. An ant that is taking the longer one, it'll take a certain amount of time, and then it'll go back. So it'll take a certain amount of time. This ant will just do it quicker. So just on the basis of that, there'll be more ants traversing the lower path. Now, if there are more ants, they will be dropping more pheromones. And so the scent there will get stronger and stronger. Whereas the scent on the top one, since it has fewer and fewer ants, it'll basically fade away. And so what you will find is, eventually, you will just have ants going on the shorter path. So it's a very interesting idea that is actually used by humans to find shortest path optimization algorithms when you go up in math. So people have actually taken this idea from ants and used it in algorithms. So that's kind of interesting. So what I'm going to do now is, I know we have, how much longer? Because I want to leave 10 minutes? Okay. So I'll tell you a little bit more about another topic. And then if there's time, I'll show you just a tiny bit of one more thing, because I do want to leave time for questions, because that's the most fun part. So this is how, the Big Bang of numbers, I want to tell you where that came from. So this was in Bombay, which is now Mumbai. I was a student, physics major, as was pointed out, and I was sitting in algebra class, and this math teacher, Dr. Huzur Bazar, told us about this very famous saying that says that God gave us the integers, and all else is the work of man. So what Kronecker was saying was that, you have to assume that the integers actually come from somewhere. And once you assume that, then mathematicians can construct everything and really give you all of mathematics. Well, Dr. Huzur Bazar said, I can actually go better than that. I can actually do something much better. I don't even need God. I can actually create the integers myself. So this is what I call his magic trick. So what he was going to do involved sets. Now, people may have heard this term before. a set is a collection of objects. How many of you have heard that? Okay, so a fair number. A set is just, we can talk about the set of people in this room. We can talk about the set of chairs in this auditorium. It's just a collection of objects. So often a set is denoted by a diagram where you have a boundary and then you have objects inside. You can have a set of cats, a set of mice, whatever. Now you can also have a set that is completely empty. For example, the set of all integers that are positive and are less than -1. No such thing. So that's an empty set. Set of all trees in my backyard. I don't have a backyard, so it's an empty set. Set of all honest politicians. That's a cheap joke, but I always gets a laugh. So what you do is you start with a set that is empty, and this is called the empty set. And so what Dr. Huzur Bazar said was, I'm just going to define this to be the number 0. So this is how mathematicians actually construct something out of nothing. This is a very exciting thing. If you look at religion, for example, they keep talking about creatio ex nihilo, which means creation out of nothing. God is supposed to have created the universe out of nothing. You also see it in physics, where the universe is supposed to have emerged from a singularity, which is almost nothing. So mathematicians start with the empty set instead. Once you have this 0, then consider the following. And again, I'm giving you this example to just show you how ideas are so central in math, and it's not so much just about calculation. Suppose you take a set containing this empty set. Okay, so you have something called the empty set, which is just this dotted thing, and then you construct a set which contains that. So now think about the outer set. Is that empty, or does it actually contain any objects? Well, if you think about it, this outer set does contain a single object, and that is the empty set. So you can't say it's the same as an empty set because it actually has something in it. And so what you do is you equate that to be the number 1. So you start with 0, empty set. Number 1 is going to be a set containing the empty set. And now what you can do is you can place these two side by side. There is my 0, there is my 1. And then take a set that wraps around both of these. So now I have a set, a new set, and notice that this set has the numbers 0 and 1 in it. How many objects does it have? 2. So that's what I'm going to define as my number 2. So once you get into this process, notice that I can start defining more numbers. I can define the number 3, I can define the number 4, I can define, keep going on. And notice that each set that I've defined has exactly the same number of objects as what I define it to be. So set 3 has 3 objects, set 4 has 4 objects. This is how mathematicians and Dr. Huzur Bazar created the numbers. But once this happens, notice what I can do. These numbers just start following from each other. So I love that special effect. So that's the Big Bang of numbers. And basically, what you can do is, just starting for nothing, you can make all the numbers come into being. And what the idea of my book is, hey, once you start with this Big Bang of numbers, then what you do is, from just the regular numbers, you create all the other numbers that you might need in your universe. It's very playful because these numbers have personalities and so on. And it's also very interesting because you end up with, think of, the whole idea is, how would you actually create the universe as a mathematician? Everyone is familiar with the number pi, for example. Number pi just keeps going on, doesn't repeat. And what would such a number be useful for? Well, most people would say that, having a number that never repeats it would be useful for getting the exact value of pi. But that's not, if you're the creator of the universe, maybe you don't need such exactness. NASA, for example, only uses pi to about 12 decimal places, and that's enough for all their purposes. So the real use for a number like pi, which never repeats, is that when you start looking at its decimal expansion, you get this idea of randomness. And that is very essential for your universe. So you get a new twist on things. And just one last thing, one or two things I'll say. And the first thing is that I've divided this book up into days, just like the days of creation. And the day 1 is about the numbers. Day 2 is about geometry. And everything starts with a point. This was something by famous artist Kandinsky. And you can actually create all of geometry just by a single point. You start joining points together, you get a straight line. If you start stacking straight lines, you get a plane. If you start stacking planes, you get 3D space. And if you think about it, what would happen if you started stacking 3D space? Well, we can't really think about it because we are stuck in 3D. But essentially, you could sort of wrap your minds around this idea that you would get 4D space in some sense. And this is one of the big advantages that math allows you to do. It allows you to think about things that you might not be able to visualize, but you can still logically get to that kind of conclusion. Okay, so there's a whole bunch. This talk could go on for another hour. I'm going to actually show you one last thing, and that is whatever happened to the letter that I sent, to the book that I sent to the Pope. So this was many days, actually about a couple of months later, because I mailed it off to the Vatican. So a couple of months later, I got this response. And the envelope came, and I was my hands were almost shaking. I was wondering, hey, is this going to be from the Pope or from his lawyer? Saying that you've used him as a character. But as you can see, he's received my book. He's asked he thanks me, appreciates the sentiments, and it was very positive. So the Pope is all for the Big Bang of numbers. So thank you, and I'm happy to answer questions.
So this was fascinating and enjoyable.
Thank you.
I'm an artist, but I have a great appreciation for mathematics. And that's something that I come across over and over again, and is fascinating to me, is the question of that a lot of people debate: is mathematics or numbers, are they things that are discovered or invented?
That's a great question. I even have a slide for that. So that's perfect. Thank you. And I didn't pay you or anything to ask that question. Okay. So this is an eternal question. Is mathematics something that is created or invented, that is discovered or invented? And it goes back to Plato, who thought that mathematics, all of mathematics, was something, every math theorem, every number, every algebraic expression lived in a separate universe. All these were actual entities that lived in some universe. And as human beings, the clouds would occasionally part, and we would get some sort of idea of these equations and these theorems, and so we would somehow discover them. Much like we would discover biological specimens or chemical elements and so on. So that's one way of looking at mathematics. The other way of looking at mathematics is that it's entirely a human invention. That if humans did not exist, mathematics would not exist. That 0, 1, 2, like Dr. Huzur Bazar said, were all things that we do. And this actually is something that I keep working with in the book, because I keep pointing out how math is more of an invention, but also it can be a discovery. And it has this dual personality. And the eventual question is, and here's my slide. Let's see if I can pull it up. So the eventual question comes to, is mathematics something that we just do in our minds, and you need this human element, or is mathematics something that just occurs spontaneously in the universe? This is something that, if it occurs spontaneously in the universe, it doesn't particularly have any purpose, right? It's just happening and it's out there and so on. If it's happening in our minds, then it has a purpose. Then that's what we use it for. So the question can be kind of, it's parallel to this question that talks about our own existence. Are we here just by chance? We're just some artifacts of the universe that just popped up and we're here without any necessary purpose? Or is there, perhaps a supreme being or some other entity or some other force that is actually, our existence is something that really depends on that and has some purpose to it? And that's a question that we can never really answer. It's, people will be divided on it till the end of time. So mathematics, in some sense, is a metaphor for that question. And it kind of tells us that, hey, with this most perfect thing that we know, we can't really answer that question. So we shouldn't expect to be able to answer it for our own existence either. So I kind of try to match those two metaphors and basically say that you can't really answer that. Okay. Other questions? Yes. If you either you can just tell me and I'll just repeat your question. Yeah. So where is the origin of pi? This is a great question because, as you know, March 14th is called Pi Day because it's 3.14. That's the beginning of the expansion of pi. But where does it come from? Now, when I was a kid, I was taught that pi was 22/7. That was the exact answer, and 3.14 was an approximation. And that's not true. It took me, it's just like discovering that there's no Santa Claus or something. That pi is not 22/7 because you always thought that was true. So pi is an irrational number, and where does it come from? Well, one of the ways that you could define pi is that it is the ratio of the circumference to a diameter of any circle. The problem with that definition is that a circle is something that you can't actually physically draw. You can never draw a perfect circle. You'll always be a little off. So you wouldn't be able to actually measure pi that way. If you want to actually measure pi, then you have to come up with different series. There are all these mathematical formulas that sum up to pi. There are these series of numbers that end up giving you pi. And this is something, if you think about it, this is one of the most fascinating things about mathematics. Here is pi that you ask where does it come from, and it really comes from geometry, right? You're looking at circles. You are finding just this amazing fact that the circumference divided by the diameter is always the same number. And if you could measure it exactly, if you had a perfect circle, it would be 3.1415, whatever. And then here are all these formulas that have nothing to do with circles. They come from calculus, and they come from infinite series and so on. They're purely abstract things, no geometry involved. And suddenly, these formulas also give you pi. This is one of the most fascinating things about mathematics because you find that there are connections which shouldn't be there. There's no reason for these two to be connected. It's similar to things like, think about you're talking about circles, they're conic sections, right? There's a parabola, there's ellipses, there are hyperbolas. The ellipses in particular, all these were discovered by the ancient Greeks, and they were doing abstract stuff and coming up with these shapes. Well, hundreds of years later, Johannes Kepler was able to use those same formulas to show how the universe, how the patterns, how the planets revolve around the sun. He found that they move in elliptical patterns, and comets move in parabolas, perhaps. Again, something that has no connection, has nothing to do with our real universe, turns out to have a complete, immediate application in our universe, to describe our universe. So this is one of the big fascinations of mathematics, why something that is so abstract is so good at defining the universe. And it's often called the unreasonable effectiveness of mathematics in describing our universe.
So thank you for coming to Geometry. I'm not a student or a faculty, but I just live nearby.
Great.
You'd hinted at building a grassroots effort for making math more, I guess, you know.
Yeah, popular.
In Germantown, we have an arts museum, but we have nothing around math.
So the question is, what can we do as a community to have a grassroots effort in math? And to tell you the truth, it was really something that I've probably been doing myself, mathematical outreach. But I have to admit that it is this symposium that started me thinking about this. So I haven't got all the answers yet, but I do feel there is something there. And this 58% of people who enjoyed math classes, that's something that really we should somehow be able to harness that energy. And I'm open to suggestions. My email is suri@umbc.edu. I'm thinking about these things. I just was saying right before coming here, I was writing an article about this. So hopefully that'll be out there in a couple of days. But I'm looking for ideas myself. And I don't know. I mean, I've never been a grassroots activist, so I need help from people who are good at that. So that would be great if something can be started. And I'm looking for an email from your group. So I'm not going to leave you. So you have to tell me. So let me know. Yeah. Yes.
So I was wondering, so you brought up the example of the shells and the patterns. I was wondering if you would show, like, would there be a resemblance of knowing a pattern in, like, the pattern of cheetahs?
I'm sorry, a same pattern of?
Of cheetahs.
Of cheetahs.
Yeah. So would there be a mathematical way of conducting that kind of experiment?
Yes, that's a great question. Cheetahs have the, like leopards, you mean? I think you mean leopards and so on. Leopards, cheetahs, tigers, zebras. How do all these patterns come up? Well, interestingly, this was first discussed by a very famous person who you probably may not realize was doing this kind of work. But this was Alan Turing, who was the person who was, you might have seen the movie Enigma. He was responsible for the code breaking and so on in World War II. So he actually wrote a seminal paper where he looked at this very question: how do patterns form on shells, on leopards, on whatever? And he was able to describe it all. The model that I gave you was a very simple one. He used differential equations. And basically, his idea was that there is something that is an accentuator that is increasing the amount of dye or pigment, and there's a suppressor that suppresses it. He was able to model this, and with it, just by changing slight parameters here or there, he was able to come up with all these patterns. If you change the parameter a little bit, you get stripes. If you change it in this direction, you get dots. If you change it a little more, you get some other pattern. So it is actually, you can describe all these patterns using mathematics. And there are different models of doing it.
You mentioned eventually they figure out ultimately this is the.
Yeah, so your question, just to summarize, is just like with the ants, similar effects seem to arise with human beings too. And maybe in nature as well as more generally. And are these the result of some intelligence, perhaps, or the result of just something that happens by chance? At least in animals, this is the example of the ants is usually called swarm intelligence, like the way bees will build, nests and so on, or the way that various other structures will arise. The technical term given by mathematicians is called emergence. So these are called emergent phenomena, where instead of an artist deciding where he's going to draw something and being the mastermind behind this picture, somehow the picture just emerges with some very simple rules. And this is very interesting that you can have this great increase in complexity occur with very simple rules. Look at the example of the shell as well. It was just this very simple rule, and you got this very complex behavior. This has often been advanced as a partial answer to how life itself might have emerged. That it's a process that involved very simple calculations, simple interactions, and that led to more and more complexity and gave you, full-fledged life. My favorite example of this kind of emergence is the following. Supposing I took a whole bunch of people from here and asked you to stand at one spot, but you were just facing all different directions. So randomly people were facing different directions. You were all standing at one spot. And I said, okay, all of you now, keep facing the direction you are. Just move forward by about 2 feet. What do you think will form? You'll get a circle. Because, random directions, if you have enough people, they all move forward 2 feet, and what you'll get is a circle. So that again shows how through randomness, giving a simple rule gives you a pattern. So that's what's fascinating about just about everything we see. If you delve deep enough, chances are you will be able to find something that is explaining that in a mathematical way.
How can we make this more pattern-centric?
So I guess the main question is, how does math, patterns, and AI sort of interact? Where in this trinity, and certainly there have been great advances in AI, and we can certainly expect more and more. One thing that has happened is that there are now assistants, proof assistants, automatic proof assistants that allow you to basically come up with proofs to theorems using AI. A lot of it is still pattern recognition, where they will look for, maybe it has in its memory how to prove a theorem. ChatGPT will actually prove some theorems for you, but not all of them. There is also something called automatic theorem proving, where with mathematicians guiding the software can come up with different proofs. And what's done for that is that a lot of basic theorems are fed into this program, and then based on that, you can find logical deductions and try to prove things. The one thing that's very weird about these proofs, some of these proofs that have emerged, is that humans can often not understand them because they're so, they have so many lines of code and so many steps and such convoluted ways that we aren't able to understand that. And one of the questions that then arises and has arisen in conferences is that, is this what we want? The fun of doing mathematics is to appreciate proofs, for example, as a form of art. Mathematicians will often talk about an elegant proof. And so if you are, if like 50 years from now, you can just put in a conjecture, crank the machine, and out pops a proof, which you really can't appreciate on any aesthetic level, is that really, how does that square with the idea of mathematics and art? So this is something that we just have to see where things evolve. Usually humanity finds a way to make things interesting still, because mathematics, for most mathematicians, is a game, and just pressing the button isn't such a fun game. So I'm hopeful that we'll find some good way. Okay, thank you.